All right, great. So our next talk in this session is on clamping variables and approximate inference. And it's going to be by Adrian Weller and Tony Jabara. And Adrian is giving the talk.
Good morning, I'm Adrian Weller. This is joint work with Tony Jabara from Columbia University, who's also here. I'm going to be presenting highlights from our paper, and if it's interesting for you, please do go to this website. You can download the slides and follow along. Please take a look at the full paper, and also please come to see us at the poster session or any time. So I'm going to be talking about undirected graphical models. These are a powerful way to represent relationships across variables with many applications, including computer vision, social network analysis, deep belief networks, protein folding, and many others. And in this talk, we're going to focus on binary pairwise models, sometimes called easing models. So these are models where each variable can take one of just two possible values, and between any two variables, we might have an edge. That edge can either pull the variables towards the same value, in which case we call it attractive, or it can push them apart to different values, in which case we call it repulsive. So let's look at some examples. Here at the bottom, we have a typical grid from a computer vision application. Here, each variable would represent a pixel. And because in the real world, objects are contiguous, suppose we're trying to identify whether pixels are foreground or background, they're likely to take the same value if they're adjacent to each other. So all the edges here are attractive. And if we have a model where all the edges are attractive, we call that an attractive model. So here's another example. This is part of a social network where the variable would represent the preference of an individual, perhaps for a controversial topic. So an individual might be perhaps a frequentist or maybe a Bayesian. And we're showing edges here that are blue for attractive edges, which would represent the idea that perhaps people who are friends with each other might pull each other towards the same preference. And the red edges are repulsive, showing that maybe if people don't like each other, they push each other apart to different preferences. So we have both kinds of edges here, and we call this type of model general. This is a third example. At the top here, we have a very small restricted Boltzmann machine, where the green variables on the bottom are observed, and the red ones at the top are unobserved. And here, the edges could be attractive or repulsive, so it's another example of a general model. And for all of these models, the fundamental problem is marginal inference. So that's the problem of estimating the marginal probability distribution of just one variable, where you see we have to sum out or marginalize over all states of the other variables. It's closely related to computing the partition function, which we'll define in a minute. And these problems are computationally intractable, so there's a lot of focus on approximate methods. In this talk, we'll show that combining the method of approximating these things with clamping variables, this can be very fruitful for marginal inference. So it's a quick outline. Next, I'll give background on inference and clamping. And then I'll show our main results, which indicate that combining clamping variables with variational inference, we obtain strong theoretical results and promising empirical results. So first, I'll give a brief introduction to binary pairwise models. We have naturally binary variables with pairwise potentials. And I'm going to write theta to represent the set of all the potentials. We'll write x for one complete configuration of all the variables. And I'm going to use this shorthand notation, theta.x, for the total score, taking into account all of the potential functions. And for those who are familiar, this is the standard over complete representation. Then the probability distribution is given by this expression in the middle. The probability of any particular configuration is proportional to e to the score. But in order to ensure that we have a valid probability distribution which sums to 1, we need to compute this normalizing constant, written as z, which is the sum over all states of e to the score. This is called the partition function, which is a fundamental quantity we'd like to compute or approximate. So thinking of approximation, let's look at a variational way of thinking about this. So it's well known that exact inference may be viewed as optimization, where log of z, log of the true partition function, is the maximum over all probability distributions that are globally consistent with the variables of the expression in the brackets, which is the expected score plus the true entropy. And in this talk, we're going to focus on an approximation which was introduced by the physicist Hans Bethe, who's looking down from the top right corner. And this is a pairwise approximation where we define log of zb. Zb is what I'm going to call the beta partition function. It's defined in a very similar way, but two things have changed, indicated in blue. So instead of the true entropy, we use the beta pairwise entropy approximation. And we relax the space over which we optimize to a more tractable space, which is all of the marginals that are pairwise consistent. Okay, and this beta approximation is in very widespread use, even for those of you who haven't heard about it. So loopy belief propagation, which many people use, can be thought of as a heuristic to try to perform this optimization. And when it converges, it finds fixed points of this beta expression. It's well known that on models which have no cycles, acyclic models, the beta approximation is exact. So there we have ZB equals Z. And on the other hand, if we're looking at models which do have cycles, the beta approximation is often very accurate, but typically we don't have any guarantees on that. In this talk, we're going to show that we can derive both upper and lower bounds on the beta partition function compared to the true partition function. So let's talk about clamping. We'll refer a few times to this model topology up on the left here. So I'm going to call this a lamp because it looks a little bit like a lamp. And to compute the partition function z, the brute force way to do that is to write down all the different configurations. For each of them, write down the score, write down e to the score, and add them all up. Okay? Or we can think about splitting z into two parts. So we can clamp a variable, as shown here, variable x1, to each of its possible values, and then add together the two subpartition functions corresponding to each of those values. So here you see in the table, the gold configurations are all the ones where x1 equals 0, and the pink ones are the ones where x1 equals 1. And clearly, when we add those two together, we'll get the same original total. And when we're looking at those subpartition functions, after we've clamped a variable, because it's held to a fixed number, we can, it doesn't influence the computation, and we can remove it from the graph. Okay? Now, after removing the clamped variable, if the remaining submodels are acyclic, then we can find those subpartition functions efficiently. So we can use belief propagation, or as we said before, the beta approximation is exact on models without cycles. What if it's not? Like in the example here at the top, you can see it's not quite acyclic. So there are two things we could do. We could repeat this process, so clamping and removing variables until the remaining model is acyclic, or we could settle for approximate inference on those submodels. So you see this red expression, which parallels the expression above. Here I'm introducing a new concept, which I'm going to write ZBI. So that means what we get when we clamp the variable xi and sum the approximate subpartitions, where we run the beta approximation on those submodels. Okay? And here's a question. Will this always lead to a better estimate than approximate inference on the original model? Any guesses? We have one yes, and it's great intuition. Interestingly, it turns out that very often it does, and we'll prove it does in some situations, but actually not always. And if anyone's interested, we have a counterexample which shows that actually clamping any variable makes it worse, which is quite interesting. So now let's look at a variational perspective on clamping. We have the beta approximation that we defined before, and just make this simple observation that when variable xi is clamped to a value, we can think about that as doing the same optimization, but over a subset. Okay, so log zb conditional on xi equals 0 is maximum of the same thing, but here we're constraining to one particular slice where the singleton marginal of variable xi is set to 0. So because we're maximizing over a subset, of course, the value is going to be upper bounded by the unconstrained maximum. So zb conditional on xi equals 0 is upper bounded by zb. And similarly, if we condition on xi being 1, we have the same upper bound. So at the bottom here, I just have a recap of notation, and please try to stay with me on this because we're going to use these terms a lot. Z is the true partition function. ZB is the beta optimum partition function. And remember, I introduced this ZBI, which is what we get when we clamp variable xi and we sum the approximate subpartition functions. Okay? So we're going to go from that simple observation to showing a simple upper bound, well, actually quite a helpful upper bound on the true partition function. So let me just go back again. Remember, we've defined ZBI in this way. We're summing these two terms. And just above, we showed that each of those two terms is upper bounded by ZB. So almost trivially, we have that ZBI is upper bounded by 2ZB. Okay? But now we can repeat this process. So keep clamping and removing variables until the remaining model is acyclic. And when we've done that, the beta approximation is exact. So for example, if we have to delete two variables, like we have to do in the lamp model at the bottom, we obtain ZB ij, which is the sum over all the subpartition functions where variables xi and xj are set to all their possible different values. Each of those, again, is optimizing over a subset of the total. So each of those is less than zb. And so that's less than or equal to 2 squared, or 4zb. But now that the insight is that each of these subpartition functions is on a model which doesn't have any cycles, so it's exact. So let me just say that again. Each of these conditional zb's in the middle is equal to the conditional true z. And when we add up the conditional true z's, it's just like we did before when we had the gold and the pink. When we add up conditional true z's, we get the true total partition function z. So the left-hand side here is actually exactly equal to z, and we get z is less than or equal to 4zb. So in general, we can do this on any model, and the bound we get is going to depend on how many variables you have to remove from a model to get an acyclic model. So the minimum number of variables you have to delete in order to get that that's the minimum size of what's called a feedback vertex set. So if we call that nu, then we have this theorem that z is actually less than or equal to 2 to the nu zb. And perhaps surprisingly, actually, this result is tight, which we can talk about if you're interested. Just to review what we've done, we made a simple observation which gave us an upper bound on zbi. Again, zbi is what you get when you clamp and sum the approximate subpartition functions. And then we repeated until the remaining model is acyclic, where the beta approximation is exact. And that gave us an upper bound on the true partition function. So can we go the other way? Can we find a lower bound on zbi to get a lower bound on the true partition function? And it turns out that we can for the particular class of attractive models that we introduced at the beginning. So again, an attractive model is one where all edges are attractive. We show in our paper a theorem that for an attractive binary pairwise model and any variable, when you clamp and sum the approximate partition functions, you can only increase the beta approximation. And then, using exactly the same argument as before, we get a new simple proof that for these models, the beta partition function is upper bounded by the true partition function. Okay, and this was a very big result, which was conjectured for a while, but only proved recently by Ruozzi. He proved it with an elegant method of graph covers, but that was a little foreign to some people in the machine learning community. So here, our method builds from first principles, just looking at derivatives of the beta free energy. And because here we've shown that every time you clamp and sum, you can only increase, and we've got at the top an upper bound of the true number, that means that every time you clamp and sum, you can only improve the estimate, the beta estimate of the partition function. Okay, so this is a class where we've proven that's true. Let's look at some experiments. Here we're going to be thinking about which variable should we clamp in general. So we're going to compare the error of zbi, based on clamping different variables, to the error you get with the original zb for various ways of choosing a variable to clamp. First, we're going to explore what's the range of possible outcomes. So we'll try everything, and then with hindsight, we're going to show best clamp, which is the best improvement in the partition function estimate. We'll also show the worst improvement, and we'll show the average. But then, maybe more interesting, we're also going to show two methods we introduce for trying to pick a good variable to clamp. And the intuition for these is that beta is exact on models without cycles. So what we'd like to try to do is to break tight, strong cycles. And one simple way to do that, we call max W, is just to look very locally and pick the variable that has the maximum sum of instant edge weights. So on the lamp here, that will tend to pick variable x10, because that has the highest degree. But obviously, that's not great for breaking cycles. It hasn't actually broken any cycles. So we also introduce another more sophisticated method we call mpower, which does a better job of finding cycles. And on the lamp topology, it typically picks x1, which does better. But we'll see on some simple examples that actually they both perform well. So here we looked at random attractive models on just 10 variables, where each edge is randomly on or off with probability 1/2. And at the top, we're showing the error of the log partition function estimate. At the bottom, we show the error of the singleton marginals. The x-axis is the maximum interaction strength, and the y-axis is showing the error. So in both cases, blue is showing the original error, and then we have error for different choices of picking a variable to clamp. And the main takeaways are that clamping any variable helps significantly, and that our selection methods perform well here. So that's encouraging. So this is for attractive models where we've proven that we should expect some improvement. What happens when we look at general models? So this is the result for general models, and very interestingly, actually, qualitatively, the results are really very similar. You get an improvement no matter which variable you clamp, although it's not great if you pick the worst one. But still, if you use our heuristics for picking a variable, then you get a very dramatic improvement. And interestingly, these results remain promising for higher n, which we can talk about if anyone is interested. So let me just finish by recapping our theoretical results. We made a simple observation on a variational view of clamping variables to get an upper bound on ZBI. We repeat clamping, removing variables until we get a graph which is acyclic, where beta is exact, and that gives us an effective upper bound on Z, the partition function. Then for attractive models, we have a theorem which gives a lower bound on ZBI, and then we use the same argument as above to give a simple new proof that, in this case, the beta partition function lower bounds the true partition function. And we also show that clamping any variable and summing can only improve the beta estimate. And in fact, to prove this theorem, we derive a stronger result, which you might think of as a master theorem for our attractive model results. And that's an interesting result which shows convexity of a function. So if you're interested in that, please come to our poster, and we can tell you more details about it. Thanks very much.
I have a quick question. So for a square lattice, you have to clamp almost, do I understand correctly? You have to clamp half of the, if you consider the full square lattice, full square Ising model. I mean, for infinite lattice, you have to clamp infinite variables, basically.
So so it's a good point. So this isn't going to be very helpful for all models. However, it is a bound which applies irrespective of the potential functions. Only depends on the topology, which is interesting. One thing you can easily show is actually this: the minimum size of a feedback vertex set is going to have to be lower bounded by the tree width, -1 actually. And so, grids have high tree width, and so the minimum size of feedback vertex set will necessarily be somewhat large. But still, depending on how big your model is, it may turn out to be a useful bound.
Hi, thank you for your talk. So I also have a question that ties in with that. Have you explored some hybrid methods where, depending on the local topology of the graph, sometimes you would drop an edge, like in mean field or in structured variational inference, and sometimes it's better to clamp a variable, like in your model?
I think that's a great direction to explore. We haven't done that, but I think that's very interesting.
Thanks for the really nice talk. My question was also related. So what happens when I have a very large graph and I don't necessarily want to deploy one of your strategies, and I just clamp nodes at random? Do I just do really poorly, or is it something in between?
So one thing we observe in our experiments, although we haven't experimented that much, and obviously to some extent it's difficult to test really huge models because you want to know, are you improving the error, but you don't know what the true value is, so it's hard to know that. But it looks to us like picking at random is sort of okay, but you'll do a lot better if you use one of our methods. And our methods are very quick to implement. So max W is sort of linear time, and the mPower method requires just one matrix inversion. So I would recommend trying one of those.